Hello, everybody. I want to thank the organizers for giving me a chance to speak, even though it's only remotely. I really wish I could be there with you, but yeah, it wasn't meant to be. I hope to see at least some of you in 3 weeks in Prague at the Topasin. So I will be talking about Tukey order on F sigma ideals. This is joint work with Jianliang He, Diego Rojas Rebolledo, and Slavek Soletsky. Yeah, my talk will be sort of like a little bit like Osvaldo, that I will be talking mostly about other people's work and only mention what we did towards the end. And it's not moving, something's... Oh, now it's moving. So Tukey order is tries to sort of classify directed partial orders. So let's just run quickly through the basic definitions. Partially ordered set is directed if it's upwards directed, and that means any two of its elements have a common upper bound. And in a directed set, we can talk about bounded sets, which is bounded from above. And those which are not bounded are unbounded, meaning for anything, any potential bound, there is somebody who's not bounded by it. We can talk about cofinal families, so or a dominating family, sometimes they're called. So a family in the partial order, a subset of the partial order is cofinal if every element of the partial order is dominated, is below an element of the cofinal family. And two slightly less common notions are that of strongly unbounded sets and weakly bounded. So, so what does it mean to be strongly unbounded in P? That means that any infinite subset is unbounded, and weakly bounded means that every infinite set has an infinite subset which is bounded, meaning it does not contain any strongly unbounded set. So these are sort of two orthogonal families in the power set of P. And so what is the Tukey order? So if we take two partial orders, the directed partial orders P and Q, we say that P is Tukey reducible to Q, or P is Tukey below Q, if there is a function from the smaller one to the bigger one, which sends unbounded sets to unbounded sets. Or equivalently, it's not completely immediate, but it's relatively easy to see that we can also talk about functions going the other way. Functions going from the bigger one to the smaller one, which send cofinal sets to cofinal sets. And of course, this pre-ordering induces an equivalence. So we say that two orders are Tukey equivalent if one is below the other and vice versa. Or we say that they are of the same Tukey type. So this all started with Tukey's work in 1940, where he studied convergence in a wide sense in topology. And in particular, he showed that two directed partial orders are Tukey equivalent if and only if there is another partial order into which they both embed as cofinal subsets. So sometimes we also talk, rather than saying that they are Tukey equivalent, we just say that they are cofinally equivalent. Now, much of the early work on Tukey order was dedicated to studying, classifying these cofinal types of small cardinalities. Now, if you think about countable types, then there are only two. You either have a maximum element, so the type is 1, or you don't, and then because of directedness, the cofinal type is omega. So that's easy. But for omega 1, Tukey realized that there were 5 different cofinal subsets of omega 1. Isbell under CH showed that there are at least 7. And then finally in 1985, Stevo Todorčević showed that Osvaldo mentioned this result already in his previous talk. He showed that indeed the 5 types identified by Tukey are really the only ones that you can find in ZFC. So PFA implies that the only Tukey types are omega 1, omega 1, omega cross omega 1, and finite subsets of omega 1. And he also showed that under CH you have as many types as you can have, so 2 to the omega 1. But Isbell's examples were actually interesting because one of the examples that he used was the idea of sets of density 0. So he looked at definable partial orders, even though under CH he treated it as if it were non-definable because it was just a thing of size omega 1. So that was and also motivated by the Bartoshinsky result that about additivity of measure and category. Tukey order on definable directed sets became very interesting and very fashionable. So some of the first papers were done by Fremlin, Luvoy and Berichkovich, and now there are too many other people that we would want to mention. So there is Slavek Soletsky has done work, Stevo has done work, Tamas Matra has done some interesting work, and Natasha, Dilip, and Dave Milovich and other people worked on ultrafilters, which is another interesting direction in this area. Paul Gardside and students looked more as directed orders coming from topology. There is really a lot of work being done. So a nice example of a directed family of the directed partial order is an ideal on a set. We will be only interested, well, mostly interested in ideals on omega, ordered obviously by inclusion. So the same as Osvaldo did, we assume that our ideals contain all finite sets. So that's over here. And we may need, I'm not sure, probably not, the following definitions. Well, we will be definitely talking about p-ideals, which Osvaldo already defined. So an ideal is a p-ideal if whenever we take a countable family of elements of the ideal, we can find somebody in the ideal which almost contains every element of this countable family. And as I said, definability is important to us. So when we talk about topological or descriptive set theoretic properties of ideals, we look at the product topology on the counter set on 2 to the omega, which we can shift to a topology on the power set of omega via characteristic functions, and then ideal is just a subspace of power set of omega with this topology. So when we say that the ideal is Borel analytic or F sigma, it means with respect to this this topology. Okay. Now there is a close relationship between F sigma ideals and P ideals and lower semi-continuous submeasures on power set of omega. So let's just again go quickly through the definition that everybody knows. So we take a submeasure on power set of omega where it takes values from 0 to infinity, including infinity possibly, And it's a submeasure if it measures, the only set that it measures with 0 is the empty set. It is subadditive, meaning the submeasure of a union of the set is bounded from above by the sum of the submeasures of the set, and it's monotone. So phi of A is less or equal than phi of B if A is contained in B. And it's lower semi-continuous if the submeasure of any set is approximated by, well approximated by its finite subset. So if you wish, by its initial segments. We, I think, always assume that the submeasure doesn't take the value infinity on the finite set. So all of these values of the finite sets are not infinite. And now with this definition, Mazur showed that actually all F sigma ideals are exactly the sets fin of phi for some lower semi-continuous submeasure phi, where fin of phi is simply the set of all things which have submeasure less than infinity. Okay, and a few years later, Slavek Soletsky famously showed that analytic p-ideals are exactly characterized in a similar manner, but we look at a different ideal associated to the submeasure. We look at the exhaustive ideal, which is the set of those subsets of omega, where if you look at the submeasures of the tails of the set, then the limit of these submeasures is equal to 0. And he also showed that if we have an F sigma p ideal, then we can actually find a submeasure where these two things coincide for the same submeasure. Okay. So we know how to represent F sigma ideals and p ideals using submeasures now. And so that's one class of examples that are usually dealt with. The other class of examples is sigma ideals of compact sets. So I didn't write the definition because it's roughly the same thing, only you add compact. So we are now not on omega, but we are on some Polish space, and we look at compact sets, and we want them to be closed under something is an ideal if with any two of its elements it contains their union, and it's a sigma ideal if it contains all the unions which are compact. So if we have a union of sets in the ideal, countable union which is compact, then it is also in the ideal, and it's closed downwards. So if I have a compact set in the ideal and a compact subset of it, it is also in the ideal. Now, again, Kekkeris, Luvo, and Wooden showed that there is a dichotomy for these ideals of compact sets, that every sigma ideal is either G delta or is very complicated. It's co-analytic. So another source of interesting examples is the sigma ideals of compact sets, which are G delta. So examples are the nowhere dense ideal of subsets of nowhere dense subsets of the Cantor set, or the ideal of closed measure zero subsets of the Cantor set. I included another ideal I0, which I will not define. If you want to read it, you can read it, which was introduced by Justin Moore and Slavek Soletsky to disprove an early conjecture about, they were just wondering whether the nowhere dense ideal is actually maximal in the Tukey order about all these sigma ideals of compact sets. It turned out that it's not. So the usual study of Tukey order on definable structures uses this picture where the left column, where we have these sigma ideals of compact sets, is referred to usually as the measure leaf of the Tukey order. And the right-hand side, where we have examples of analytic p which sometimes is denoted as L1 because of its affinity to the Banach space L1, is the set of those subsets of omega such that the function 1 over n, or 1 over n plus 1, 2, so that we don't have to worry about 0, sums over the set. And the density 0 ideal, which was the one considered, as I said already by Isbell, is the set of those subsets of omega such that if we look at the relative density of the set as we go towards infinity, it goes to 0. And, well, of course, omega is represented by finite sets, so that's another P ideal. And omega to the omega, we can think of it as functions from omega to the omega ordered by pointwise domination, or we can think of it as the ideal of empty cross fin, which is everything below a graph of a function ordered by containment. So, so this is the standard picture of what people see as sort of a grid to which we compare things in this Tukey order. And so what about F sigma ideals? So there are some F sigma ideals in the picture. So this top element, I didn't talk about that. So this is a Tukey top element for things of size continuum. It's naturally represented by all finite subsets of the reals or finite subsets of any set of size continuum, but it can be also represented by an F sigma ideal on a countable set. Just take all branches through a binary tree and ideal generated by those. So that would be a top element. And how do you recognize that your directed set is Tukey top? Well, you just have to find a strongly unbounded set of size continuum. And then if it's size continuum, it has a strongly unbounded set of size continuum, it's Tukey top. All right, and as I said, omega is just anything of which has a countable cofinal set, in particular finite subsets of omega. So among all of these things, there are only three things which are F sigma. It's this guy on top, L1, and omega. All right, so really the Tukey order on the study of Tukey order on F sigma ideals started with Louveau and Velichkovich, where one of they proved many things, so I'm not going to be very, very selective about what I will take away from their paper. So in particular, they show that if you take any analytic ideal on omega, then either it sits on top of omega to the omega, or it is F sigma. And they showed, actually, they gave an example of an ideal F, which is F sigma, which is not on top of omega to the omega. We will see that example in a bit. And it is clear that if an ideal is sigma weakly bounded, meaning a union of countably many weakly bounded sets, then it cannot sit on top of omega to the omega. And they actually conjectured that this is equivalent, so that for an F sigma ideal, either you are on top of omega to the omega, or you are sigma weakly bounded. They actually proved the conjecture assuming the continuum hypothesis, but as such, it is open. Actually, my talk when I planned speaking about this was centered about proving this conjecture, but very recently I found a gap in my proof. So hopefully it's still fixable, but the conjecture as it is now is still open. And now, so much of what I will be talking about is trying to analyze the structure of these ideals which are sigma weakly bounded. So Louveau and Velichkovich gave one example Tamás Matrai gave a lot of examples. So he showed that there is the structure of these ideals is very complicated. So the structure of P omega mod fin can be embedded into these sigma weakly bounded F sigma ideals ordered by the Tukey order. And in a paper with Diego Rojas and Indra Zapletal a few years ago, well, maybe more than a few, almost 10 years ago, we proved that we can actually sort of strengthen this into distinguishing these ideals not only by Tukey order, but actually by kernel invariance, that we can produce uncountably many distinct cofinalities of these sigma weakly bounded F sigma ideals. We didn't do that, but it probably could be even shown that consistently there are C many distinct cofinalities. We just produced omega 1 many. All right, so in this paper that I want to talk about, we wanted to see how these F sigma ideals fit in the picture that I showed you at the beginning. And so the first result I want to mention is that the F sigma ideals don't really mix very well with these other two leaves. So in particular, if we take a sigma ideal of compact sets, G delta sigma ideal of compact sets, then there are no F sigma ideals below it in this Tukey order, unless it's trivial. So I mean, the ideal is countably generated, that means equivalent to omega. So there is nothing F sigma below any sigma ideal of compact sets. And that's about as much as we could say. Well, they also don't mesh well with well, let me leave it at that. But so we restricted ourselves to a manageable class of X sigma ideals, and also because we wanted to study these sigma weakly bounded ones. So here I will give you two. These are really the only two definitions that are new that I will mention. So we want to talk about ideals, but as I said, talking about F sigma ideals and talking about submeasures is the same thing. So I want to talk about two properties of these lower semi-continuous submeasures. So the first one is flatness. So a submeasure is flat if for every number m, we can find another number n, such that if we take any finite set A, which has measure less or equal than n, we can go far enough, so there is a j, such that if we take any set of submeasure at most m or less than m, above B, which live above B, above j, so they are very, very far away, then they really don't add anything to the measure of A. So the submeasure of phi of A union B is still less than n. A somewhat stronger property that we worked with in this paper with Indra Zapletal and with Diego Rojas was that of being fragmented, which is what you can imagine if you want to think about these flat, is simply that for the submeasure there is a partition of omega into intervals, and the submeasure is simply the supremum of whatever the submeasure has on these finite pieces. So every such submeasure is flat, and again we call an ideal flat if it is of the fin of phi for a flat submeasure. And the submeasure is said to be gradual. So again, this one is perhaps even a little bit more complicated, but hopefully not too much. So for every m, we can find an n, such that again, if we go far enough, so the j just says go far enough. But now we take, sorry, and there is one more quantifier, so that for every L, we can go far enough. So there is, so let me try again with the quantifiers. For every n, there is an n such that for each L. So M, we think of as a submeasure of pieces. N is the target submeasure that we want to have. And we roughly want to union up as many things as we want. So that's what the L represents. So now it says that if we go far enough, so there is a J, and we take L many things which live above past J, and each of them has submeasure less than M, then their union has submeasure less than M. Okay, so that means, again, if we want to take unions of as many things as we want of small submeasure, which is M, then we can uniformly bound these things by some number N, and we can take as many of them as we want as long as we go far enough, right, far away from zero. Okay, so hopefully the picture is not terribly bad. And we call a submeasure gradually flat if it is both flat and gradual, and we call an ideal gradually flat if it is fin of phi for some gradually flat lower semi-continuous submeasure. So the point of this is that all gradually fragmented ideals are sigma weakly bounded. This is very easy to see and sort of the point of graduality. And all known sigma weakly bounded ideals are gradually flat. Now we proved a dichotomy for these flat ideals that either they are gradually flat or they are top. They are way up there. And it's sort of curious that sometimes it's not immediate to see which one is which, because so if you look at, so I have these two ideals. P is the one defined by Luvo and Veličković in their paper. So this one is gradually flat. It's the one set of those subsets of omega which sort of grow polynomially. But if you just say, look at those subsets of omega which grow linearly, so you just change the function which tells you this, the rate of the growth here, then P is gradually flat and L is equivalent to Tukey top. So they are really different. And now these gradually fragmented ideals are really the things which are sort of, which in the picture would sit down, not above omega to the omega. So for them, it's equivalent. It is for flat ideals, it's equivalent to be gradually flat, to be Tukey below density 0, to be Tukey below the summable ideal, to be sigma weakly bounded, or not to be on top of empty cross fin. So for these flat ideals, we could also prove that they don't really want to have anything to do with the measure leaf either. So again, if you have a flat ideal, then it is not even basic in the sense of Solecki and Todorcevich. I won't give you the definition because I'm slowly running out of time. But it just means that these gradually, these fragmented ideals do not really interfere with the measure leaf either. So if you take a look at the picture, sort of augmented a little bit now. So the red ideals are the ones which are F sigma. So there is this category leaf, the measure leaf, and now as far as we know, F sigma ideals are, well, there is the trivial one, the ones of countable cofinarity are down here. Then there are the sigma weakly bounded, which sort of sit to the side here. And yeah, as far as we know, all the known examples are gradually flat. And then there are the F sigma P ideals, which sit somewhere, well, they sit below L1, but sort of very close to it. And then there is the top. And this is as much as we know. So the open problems are really, we need more examples of Tukey types of F sigma ideals. But to test those examples, I will pose some open problems. So the first one is I will repeat this Lvov-Velichkovich paper, which just says that whether everything is either on top of omega to the omega or it is sigma weakly bounded. The sort of bold question is, are all sigma weakly bounded ideals gradually flat? Well, all the ones we know are, but it's probably false, but as I said, we want more examples. And then I would assume that there are no F sigma ideals below Z0, which are not sigma weakly bounded. So that's sort of the next question. And finally, we don't know whether there are any F sigma ideals in this interval up here. So strictly between L1 and the Tukey top. So Tamás Matrai has a beautiful analytic ideal, which is at least consistently in the middle here. And I remember he told me that he believes that there should be F sigma ideals, but yeah, he's since left mathematics, so I didn't have a chance to ask him what he really meant. So there is that problem, which I think is very interesting. And finally, I want to repeat the question, which is from Isabel's first or second paper on Tukey order, which concerns ultrafilters. So it is still unknown whether it's possible that all ultrafilters are Tukey equivalent. And there are more experts on this in the audience there. So if somebody wants to know about that, ask Natasha, for instance. And that's all I wanted to say. Thank you.